In this video, I'll be discussing how to construct an orthogonal basis of an inner product space. The prerequisite of this topic is an idea of vector space, basis and dimension of vector space, linearly independent set of vectors, and inner product space. Before going to the construction of orthogonal basis, let us have a quick glance into the definition of inner product space. Inner product on a real vector space V is a function that assigns a real number to every pair of vectors in the vector space V, such that the following axioms are satisfied. Here, this plus is the vector addition in the vector space, and this is the scalar multiplication in the vector space, whereas the plus sign here is the addition of real numbers, and this is a real number multiplied by a scalar r. The vector space V together with the inner product defined is called an inner product space. One example of inner product space is a Euclidean space with dot product defined as the inner product. For example, you consider R2 with dot product defined as the inner product. Then for any two vectors in R2, say x vector which is x1, x2, y vector which is y1, y2, the inner product of x vector, y vector is the dot product of x vector and y vector, and which we know it's equal to x1 y1 plus x2 y2. These are the examples of inner product space. There is another example, the set of all m by m matrices with inner product defined as inner product of two matrices A and B is trace of AB transpose. And the example is set of all continuous functions defined on the interval AB, where the inner product is defined as integral a to b f of x e of x dx. These are few properties of the inner product space. The length of a vector in an inner product space is called the norm of the vector, and it is the square root of the inner product of vector with itself. For example, if you consider the inner product space R3 with dot product as the inner product, you consider a vector say 1, 3, 2 in R3, then the norm of the V vector is equal to square root of the inner product of V vector with itself, which is going to be the square root of dot product of V with itself, which is 1 plus 9 plus 4, which is equal to square root of 14, and this is the length of V vector. So if dot product is the inner product, thus norm is same as our modulus of a vector in the Euclidean space. every vector in the inner product space with norm is equal to 1 is called a unit vector. Now, let us recall the definition of orthogonal vectors. A set of vectors is an orthogonal set if 0 vector does not belong to the set and the inner product of every pair of vectors is 0 for I not equal to j. In addition to the two conditions, if each vector is such that the norm is equal to 1, then the set of vectors is said to be orthonormal set. For example, we know that in the inner product space R2 with dot product at the inner product, the unit vectors 1 0, E2 vector is 0 1 are orthogonal vectors. They are perpendicular to each other. This is 1 0, this is 0 1, this is our E1 vector, this is our E2 vector. Now we know that the length of E1 vector is 1 and the length of E2 vector is also 1 because they are unit vectors. If you find the inner product of E1 with itself, you will get it as dot product of E1 with itself is 1. The inner product of E2 with itself, you will get it as 1. So its length is also 1. Now, the set E1, E2 is an orthonormal set. Why? Because the inner product of E1 with E2, if you take the inner product of E1 with E2, it is here, since the inner product is defined as the dot product, it is the dot product of E1 with E2, which is 0. So a set E1, E2 is an orthonormal set. These are few results which you should remember in the orthogonal set of vectors. Every orthogonal set of vectors is linearly independent. And another one is, if you have a set of orthogonal set of vectors, then if you take the scalar multiple of each vector is also an orthogonal set for the scalars not equal to 0. The expansion theorem. Yes, if we have an orthogonal basis of an inner product space V and V is any vector in the inner product space V, then the expansion of V vector as a linear combination of the orthogonal basis is of this form. We know that every vector in an inner product space can be expressed as a linear combination of vectors in the basis. You consider an inner product space R2 with dot product as the inner product, and the orthogonal basis, we consider an orthogonal basis of R2. We have seen that E1, E2, where E1 is 1 0, E2 is 0 1, is an orthogonal basis. Now, if we have a V vector, say 2, 3, belonging to R2, how do we express this V vector as a linear combination of E1 and E2? So, this can be, we know that this is actually 2 into E1 vector plus 3 into E3 vector, E2 vector. Now, what is this 2? Actually, this is 2 was same as, actually this is the inner product of V vector with E1 vector divided by norm square of E vector to E1 vector plus inner product of V vector with E2 vector, E2 divided by norm square of E2 vector. Now, since E1 and E2 are unit vectors, this norm square, this is equal to 1, and similarly this is also equal to 1. And if you take the dot product of V vector with E1 vector, it is equal to 2. Similarly, if you take dot product of V vector with E2 vector, you get it as 3. So that is the linear combination. V vector is equal to 2 E1 vector plus 3 E2 vector. So this is the expansion theorem. So this you should remember how to express any vector in the inner product space as a linear combination of vectors in the orthogonal basis. Now, given any basis of an inner product space V, how do we construct an orthogonal basis? And if you divide every element of the orthogonal basis by its corresponding length, you get an orthonormal basis of the inner product space V. Now, there is a method of doing this, and this method is called Gram-Schmidt's orthogonalization process. You consider a non-orthogonal basis of an inner product space V. We call the first basis as U1. Then you must write another vector which is orthogonal to U1, which is equal to the second basis vector plus a scalar multiple of U1 vector. And this U1 and U2 must be orthogonal. So we have this A1 is equal to minus inner product of V2 vector with U1 vector divided by norm of U1 vector square. So U2 was V2 vector minus projection of V2 on U1 vector. What we do here is we fix the first vector, that we take it as the first orthogonal vector. Now V2 is not orthogonal to U1. So what we do was we take the projection of V2 on U1 and V2 minus the projection of V2 on U1 is U2 vector. Similarly, we get the U3 vector. U3 vector must be orthogonal to both U1 and U2. So u3 vector is v3 minus projection of v3 on u1 minus projection of v3 on u2. We go on this way, and the set u1, u2, u3, etc. un will be an orthogonal set. And if you divide every vector by its length, corresponding length, we get an orthonormal set of vectors. For example, in the inner product space R2 with dot product defined as the inner product, you consider a non-orthogonal basis of R2. We know that any two linearly independent vectors in R2 is a basis of R2. So let us consider two linearly independent vectors in R2. Thus, let us call this as v1 vector, this is v2 vector. Now, this is not orthogonal because 2, 2, we know that it is 2, 2, v1 vector is thus, and v2 vector is 0, 2, 0, 2 was this. This is a v2 vector. Clearly, they are not orthogonal. They are not perpendicular to each other. Our aim is to get a perpendicular vector, or the angle between the two vectors must be equal to 90 degrees. So what we do was, you can either say, let us write u1 vector as v1 vector. You are fixing at this v1 vector, which is 2, 2. v1 vector is 2, 2. Now, let us find the norm square of this vector, u1 vector. So, which is going to be inner product of u1 with itself, u1 with itself. So, which is, since the inner product we are taking it as the dot product, this is going to be 8. Now, the inner product of v2 vector with u1 vector is equal to dot product of v2 vector with u1 vector, which is equal to 4. So, a u2 vector is equal to v2 vector minus projection of v2 on u1, which is the inner product of v2 vector with u1 vector divided by norm square of u1 vector into u1 vector. So, which is v2 vector is 0, 2 minus projection of 4 by 8 u1 vector. u1 vector is same as 2, 2. So, we get it as minus 1, 1. Get it as minus 1, 1. So, where is this minus 1, 1? This. This vector, right? So clearly this is perpendicular to our v1 vector. This is our v1 vector, this is which is also u1 vector, and this is our u2 vector. Clearly these two are orthogonal to each other. Let us do a problem. Given a basis, 3 linearly independent vectors in R3, but they are not orthogonal. How do we construct an orthogonal basis of R3? So let us call these given vectors as v1, v2, v3, the same order itself. So our construction is like this. First vector u1 vector, we take it as v1 itself. So which is 1, 1, 1. Now let us find norm square of u1. Since here the inner product is not defined here, so if when it is not defined, we take dot product as the inner product. So this is the inner product as dot product of itself, u1 with itself, and this is going to be 3. Now let us take the inner product of v2 vector with u1 vector. This is the dot product of v2 vector with u1 vector. So which is equal to v2 vector is going to be 6 plus 4 plus 5, which is 15. So our u2 vector is equal to v2 vector minus the projection of v2 on u1 vector, which is the inner product of v2 with u1 vector divided by norm square of u1 vector into u1 vector. So we have all this, which is 6, 4, 5 minus 15 by 3. u1 vector is 1, 1, 1, which is equal to 1 minus 1, 0. Now u3 vector, so let us find u2 norm square, which is inner product of u2 vector with itself, which is the dot product of u2 with itself, and this is 1 plus 1, 2. Now let us find inner product of v3 vector with u1 vector, which is the dot product of v3 vector with u1 vector, which is equal to 3 plus 6 plus 9, which is 18, and also inner product of v3 vector with u2 vector. So which is the inner product of v3 vector with u2 vector. So which is 3 minus 6, which is minus 3. So our u3 vector is 3, 6, 9 minus 18 by 3, 1, 1, 1, minus 3 by 2, 1 minus 1, 0. When you simplify this, we get it as minus 3 by 2, minus 3 by 2, 3. And this set U1, U2, U3 are orthogonal. This set U1, U2, U3 the orthogonal basis of R3 and 1 by root 3 U1, 1 by root 2 U2, 1 by root 6 U3 is orthogonal. Let us consider another example. Let M22, the set of all 2 by 2 matrices, have an inner product defined by inner product of the matrix A, X and Y is equal to trace of XY transpose. Use Gram-Schmidt's algorithm to transform B into an orthogonal basis. So we are given a basis B here which is not orthogonal. Our aim is to get an orthogonal basis of M22. So let us do it step by step. First, what we do was U1, we take it as V1 itself, which is 1, 1, 0, 1. Now let us find norm U1 square, which is inner product of U1 with itself, and it should be the trace of 1, 1, 0, 1 into the transpose of the sets. So which is 1, 0, 1, 1. So trace of the product is equal to, we get it as 3. So which is equal to trace of the product. Product is let us, so we get it as trace of 2, 1, 1, 1, which is 3. Now let us also find the inner product of V2 vector with U1 vector. So which is the trace of V2 vector is 1, 0, 1, 1 and transpose of U2 vector, U1 vector. So which is 1, 0, 1, 1. So we get it as the trace of 1, 0, 2, 1, which is 2. So therefore our U2 vector is equal to our V2 vector minus inner product of V2 vector with U1 vector by norm square of U1 vector into U1 vector, which is 1, 0, 1, 1 minus 2 by 3, 1, 1, 0, 1, which is equal to 1 by 3 minus 2 by 3, 1, 1 by 3. So let us call this as U2 dash. So u2 vector is a multiple of u2 dash, because we know that if you can take the scalar multiple of a vector in the orthogonal set, it's again going to be an orthogonal set. So let us take u2 vector as 1, -2, 3, 1. This is a u2 vector. A u1 vector is this. This is a u1 vector. So we have obtained u1 and u2. They are mutually orthogonal. That is, if you take the inner product of u1 with u2, you will get it to be equal to 0. Now u2 square is inner product of u2 with itself, which is going to be the trace of u2, which is 1, -2, 3, 1. The transpose of u2, which is 1, 3, -2, 1. You will get it as trace of 5, 1, 110, which is equal to 15. Now let us also find the inner product of v3 with u1 vector, which is the trace of v1 vector, v3 vector with transpose of. So we will get it as to be equal to trace of 1, 0, 1, 1, which is 2. Now inner product of v3 with u2 vector is the trace of v3 is 1, 0, 0, 1, transpose of u2 vector 1, 3, -2, 1, which is trace of, when you multiply the two matrices, you get it as 1, 3, -2, 1, which is equal to, the trace is 2, sum of the diagonal elements. Now let us call u3 dash. So because we will not get it in a proper, we get fractions, we don't like it, so we call it as u3 dash, and u3 let us write it in a more simplified way. 1, 0, 0, 1 minus 2 by 3, 1, 1, 0, 1 minus 2 by 15, 1 minus 2, 3, 1, which we get it as 1 by 5 minus 2 by 5 minus 2 by 5 and 1 by 5. So let us write u3 as a nice form of that. 1 minus 2 minus 2, 1. Avoid fractions. Now let us find now u3. This is our u3. Now u3 square, norm square. We'll get it as trace of -5 minus 4 minus 4, 5. Check it. Get it as 10. Now, the inner product of V4 with U1, yes, the trace of 1 0 0 0 and transpose of U1 1 0 1 1, which will get it as trace to be equal to trace of 1 0 0 0, which is equal to 1. Next, the inner product of V4 with U2 vector, which is the trace of 1 0 0 0 with U2 transpose, which is 1 3 minus 2 1, and that you will get it as a trace to be equal to 1. Next, inner product of V4 with U3, which is the trace of 1 0 0 0 with U3 transpose, which is 1 minus 2 1, and you will get it as 1. Therefore, U4 dash. So let us write it as U4 dash, and the nice form you write it as U4 is going to be 1 0 0 0 minus projection of V4 on U1, which is 1 by 3 1 1 0 1 minus projection of V4 on U2, which is 1 by 15 1 minus 2 3 1 minus projection of V4 on U3, which is 1 by 10 1 minus 2 1. When you simplify this, we get it as 1 by 2 0 0 minus 1 by 2, or you can write this as 1 by 2 1 0 0 minus 1. So let us take U4 as 1 0 0 minus 1. So orthogonal basis of M22, yes, 1 1 0 1 1 minus 2 3 1 1 minus 2 1 and 1 0 0 minus 1. So orthogonal basis, it's not orthonormal, we have not divided by the length. Now let us construct an orthogonal basis of P2, the set of all polynomials of degree less than or equal to 2, in which the inner product is defined as inner product PQ is equal to integral 0 to 1 P of x Q of x dx. The basis given as 1x square. With this inner product, the basis, given basis is not orthogonal. You can check it. See, if you take it as P is 1 and Q is equal to x, then integral 0 to 1 x dx is going to be x square by 2, which when you apply the limit you get it as 1 by 2. It's not equal to 0, so which means they are not orthogonal. So let us construct an orthogonal basis using Gram-Schmidt's orthogonalization process. let us call this as v1 vector, v2 vector and v3 vector. The procedure is u1 vector, the first basis vector, we take it as v1 vector. So let it be 1. Then what we do is we find the norm of u1 vector by the definition of norm square of this, which is the inner product of u1 with u1 itself. By the definition, it should be integral 0 to 1 into 1 dx, so which is going to be 1 itself. X apply, you'll get it as 1 itself. Now let us also find the inner product of v2 with u1 vector. So this is going to be integral 0 to 1 v2 is x into u1 is 1. So we have this, which is x square by 2. Apply the limit, you get it as 1 by 2. Now let us write u2 vector. Let us write it as u2 dash. If it is not in a nice form, then let us multiply by a scalar, which is v2 vector minus v2 vector with u1 vector divided by u1 square into u1 vector. We have all this. So what is v2? X minus, we have found this 1 by 2 divided by 1, and u1 vector is just 1. So this simplifies to x minus 1 by 2. So let us write u2 vector as 2x minus 1 multiplied by 2 throughout scalar 2. So u2 vector is we can verify this as orthogonal to our u1 vector. Now let us find out u2 vector norm square. So which is integral 0 to 1 2x minus 1 the whole square dx, which is going to be, when you will get it as, when you apply the limit, you will get it as integral 0 to 1 4x square minus 4x plus 1 dx, get it as 1 by 3. Apply the limit, you will get it as 1 by 3. Now inner product of v3 with u1 vector, which is integral 0 to 1 x square dx, which is equal to 1 by 3. Let us also find the inner product of v3 vector with the u2 vector. So this is integral 0 to 1 x square with 2x minus 1 dx, which will get it as integral 0 to 1 2x cube minus x square dx, and when you integrate and apply the limit, you get it as 1 by 6 2x raised to 4 by 4 minus x cube by 3. Apply the limit 0 to 1, we get it as 1 by 6. Now u3 dash, yes, x square minus 1 by 3 into u1 as 1 minus 1 by 6 divided by norm u2 square, which is 1 by 3 into u2, which is 2x minus 1. This on simplification gives x square minus x plus 1 by 2 minus 1 by 3. Or we can write u3 vector as 6x square minus 6x plus 1. Multiplying by 6. So this is a u3 vector. Now the orthogonal vectors are 1 u1 vector, u2 vector which is 2x minus 1, and u3 vector which is 6x square minus 6x plus 1. This is the orthogonal set of